Okay, so parent and the children. So it's the family of B. And B and C as the family of C. Okay, these families B and C. So you can consider who will be the nearest family or the nearest neighbor or whatever. Okay, and if you consider the family of E, you can think about C, D, and E. All three are its family. Okay, so this is a way the graph is connected and it is giving a relation to the individual data that is being connected. You all agree with what I say? Oh.
Yes, ma'am.
Okay, so this terminology chain is a series of nodes where each successive node in the chain is connected to the previous node by an edge, regardless of the direction. As long as we say chain, it is regardless of the direction. Path is a chain with the further constraint for directed graphs. So now direction is important, that each connecting edge in the chain has a directionality going in the same direction as the chain. So once it is in the same direction, it has a direction property. If this property, direction property should be in the same direction, then only we say it's a path. So cycle, there's a path that starts and ends in the same node like a circle. A simple path with a unique nodes. Simple cycle where you except for start and end node, all nodes are unique. Okay, start and end are same node. Other nodes are visited only once. Then this directed acyclic graph, this directed graph that has no cycle, like this. Okay, so here no cycle. If the arrow goes 1, 2, 3 like this, and if this arrow comes here and this arrow goes here, then we say it's a cycle. But now this is not a cycle, so it's a acyclic. So now we are coming directly to the another terminologies, the parent and the child is a relationship in a directed graph. Only we can take. Say, if I put this only, I know that the B evolved from A. If I don't put this arrow, I don't have any idea. So, parent and child relationship in a directed graph occurs when there is an edge x1, x2 from x1 to x2, and x1 is called the parent of x2 or x2 is the child of x1. So you are getting a edge between A and B, and B is the child of A, and A is the parent of B. That's what I have put it in x1 and x2 edge, but it is following from x1 to x2. So x2 is the child, x1 is the parent. So ancestor, descendant. If you instead of talking about parent, you can generalize that as ancestor. Instead of specifying this as a child, you can specify this as a descendant. Okay, the same information is true here. So ancestral ordering is an ordering of nodes where each ancestor comes from before its representative descendant. Who is the ancestor? He will be represented first before the descendants. So when an event occurs in the first, then we say this is the ancestor. Okay. So what is the family? A set of vertices composed of X and the parents of X. Okay. I'm talking about a set of vertices composed of X. So we have some data and we have a set of vertices, but they evolved from the parent. Okay. So what is this forest? This is a directed acyclic graph where each node has either one parent or none at all. Okay, probably we'll have some example later. Tree is a forest where only one node called the root has no parent. So we have a root. In the phylogenetic analysis, we can also make a relation like a phylogenetic analysis using the Bayesian. So directed graph, if the edges are assigned with a direction. The above graph consisting of all nodes. Here A to B, H is a forest. Why? Because he has no, here A, okay, and the B and upward to everything is a forest because it's a cluster. Every node has either one parent or none at all. So every node has one parent. Every node has one parent or none. Okay. And B, C, D, E, if you see, have an one parent with each while A, F have no parent. Okay. A has no parent, F has no parent, H has no parent. This graph is not a tree because this has this connection. Because it does not meet the requirement of only one of its node having no parent. Because if only one node is having no parent, the situation will be like this. This only A has only no parent. Every other node has one parent. So then only we can say it is a tree. Otherwise, this is a forest. Okay. Now, I'm directly coming to the Bayesian network. You guys are following the introduction of the graph theory?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So now we will use another terminologies. What is being used? The structure of now Bayesian network is a DAG. Now we know. So the structure of a DAG is definitely by two sets. One is by nodes, we say vertices, and a set of edges, that is directed edges. The nodes represent the random variable because that the node can have some events, but it is variable, it is not conserved, and are drawn as circles labeled by sorry guys, I cannot continuously speak after this corona. And are drawn as circles labeled by the variable names. So every variable, you have a variable name. The edges, now you have a direct dependence among the variables because we are connecting, we are giving one direction. So it is a direct dependence. And are drawn by arrows between nodes. In particular, an edge from a node xi to node xa represent a statistical dependence between the corresponding variable. See, why it is a statistical dependence? Because the occurrence of xj depends upon the life of xi. The probability of being existing in the xi state, that only gives the output of xj. So it is a statistical dependence between the state xi to xj. Thus, the arrow indicates that a value taken by variable xj depends on the value taken by the variable xi. What does it mean? This xi influences xj. That means xi is the parent of xj and xj is a child of xi. Okay. So an extension of these genealogical terms is often used to define the sets of descendants, that is, the set of nodes that can be reached on a direct path from a node or an ancestor node. You understand? Then, from a node or an ancestor node is a set of nodes from which the node can be reached on a directed path. Okay, so the structure of a acyclic graph guarantees that there is no node that can be its own ancestor. So when you are able to see some no node, You can simply think about this as the ancestor, its own descendant. In such a condition, is of vital importance to factorization of the joint probability. There are some terms we are going to learn. What is the joint probability? What is a factorization? Everything we are going to see now. Note that although the arrows represent the direct causal connection between the variable, the reasoning process. Now, what is this reasoning? Because we have to identify a joint probability between the two states with the reasoning process. We have to justify why that probability is a joint probability. Okay, so the reasoning process can operate on BNs by propagating information in any direction. So we are talking about acyclic, so the direction can be in any direction. So for understanding the following, based on the above discussion, now we are coming into a Bayesian network. What is the meaning of a Bayesian network? Is an annotated acyclic graph that represents joint probability distribution over a set of random variables. What are those random variables? That is n number of your data. So the network, this Bayesian network, we are going to make it with a graph theory and with a, what is this, set of parameters which are highly independent in nature. So this is the equation of a Bayesian network where G is the directed acyclic graph whose nodes are this, representing the random variable, and whose edges depend on the directionality between the variables. So Bayesian is nothing but when a graph theory, okay, and the information is derived based on the graph theory and with a theta function. The graph G encodes independent assumptions by which each variable is independent of its non-descendants given its parent G. So now we are going to again have one more idea of independency. Okay, variable xi is independent of its non-descendants given its parent G. So now we are going to identify some kind of disconnection between the parent and the child. We will see in the next following slides how it is. Okay, so the second component theta denotes the set of parameters in the node. So we have a set of parameters that is being modeled using the graph, as well as once the network is done, when the graph is done, by putting the correct values in each variable and the edges using your parameters, that is your Bayesian network. This set contains the parameters for each realization of xi of xi, because this is a capital one, this xi is the component of capital Xi, is condition on the phi I, that is a product, and the set of parents xi in graph. So now we will be seeing what is this. Okay, so I think, yeah, conditional, unconditional, and whatever. Okay, so this, how many of you are aware of this probability things? How many of you are aware of this probability? Students, are you online?
Yes, ma'am.
Yes, ma'am.
Okay. Probability, how about your knowledge on probability?
Know the basics, ma'am.
You have not learned anything in probability so far?
Yes, ma'am. In maths, we learned.
Learned, right? Okay. Okay. So for simplicity, we have defined this probability, that is, we are going with a joint probability distribution over a subset V. Okay, so this pi I, if I put it, is a product. Okay, so every time for a simplicity of representation, we omit the subscript V henceforth. If xi, we have a probability of identifying every individual variable states. So you have a variable x1, x2, xn. Okay, if xi has no parents, okay, so its local probability distribution is said to be unconditional, because if you have a parent, only, you can emerge like this. But if you have no parent, it is unconditional. Okay. Otherwise, it is conditional. If you have a parent, if you have a conditional one. If the variable represents, this is one such, okay, that distribution. If the variable represented by a node is observed, means that is on, that node is working, that is in the on state, then the node is said to be the evidence node, because once an event is happening, it is observed, so it is a evidence for the relation. It's a evidence node. Otherwise, the node is said to be hidden or latent. See, in the picture, this is a simple picture. That's what everything is visible. But we may have some kind of millions of data. So you can go with a million of trees, but you can, in the middle of the trees, you can have a hidden layer. Just a minute. Okay. Okay. So what I was talking. So here, if you go with some kind of millions of data, in the middle layer, we will not worry about it. So we can say this is a hidden layer or latent layers. Okay. So these are all some of the things. So for example, see now this is your conditional and unconditional states. You have I have mentioned, right? No parents. So let us go with an example. Okay. This is one simple example where I am talking about 5 variables. There is a variable worker, there is a variable chair, there is a variable back, there is a variable sport, there is a variable egg. We don't know the relation. Somehow we derive this relation. Now you think about these variables are scattered. Okay, how we can make this directional, and it is a acyclic. Okay, so there are two things. Every state will have a probability. Okay, so this probability, okay, the probability for a chair to, if it is a true, let us put 0.8. This is optional. Okay, this is an example. If every time the probability should be 1, so for a chair, if the probability is 0.8, and if that event is to be false, then it is 0.1, 0.2, because 1 minus 0.8, that is 0.2. You agree with this? Students?
Yes, ma'am.
Yeah. So similarly, yeah, if the sport is a variable and if you give a true and the probability is 0.02, means the rest false is like 0.98. So the workers also, like you can go with the workers, the probability 0.9 and 0.1 for true and the false. And here also, egg also, you can have a probability. Okay, then probability here with the probability with the chair and the sports, it's a combination, true, 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 false, like that. So this is just a random numbers, we have given it based upon the state, just to make you understand the logic of the data network. Let's see, a person who might suffer from back injury. Okay, now we are thinking about a person having a back injury, an event represented by variable back. So this is a direct relevance. So a person, a worker, okay, anybody who can have a problem, okay, there's a back problem, okay, they can simply say that, okay, back injury means they can have a back problem. Such an injury can cause a backache. Okay, a person who can have a back problem that they can end up with a ache issue. Okay, so this is an event which is represented by ache. And the back injury might result from a wrong sport activity. So from the wrong sport activity, the back problem might evolve. Okay, or from a new uncomfortable chair installed in the office. So because of the chair also you can have a back problem. Either by a sport activity also you can have, because these are the specified variables now. And we are trying to get a connection between the given variables. In the later case, it is reasonable to assume that a co-worker will suffer and report a similar backache syndrome, and even represented by the variable worker. Okay, now there is also a problem like one person, another workers also may have the same problem because of the chair, and they can get the back problem because of that they can have the ache. Okay, so now the conditional probability table of each node is listed. Here now we have a conditional probability, because if this exists, what is the other one? So it is a conditional one. Now, in this example, the parent of the variable back are two things. Now we go back. Okay, if I say who is the parent of this back, one is the chair, the other one is the sport. Okay, I think, can I paste this here? Okay, the child of back is ache. Okay, so ache is a child of back. And the parent of worker is chair. So who is the parent for the worker? Because from chair only it is evolving. So this is the child, this is the parent. Following the Bayesian independent assumption, several independent statements can be observed. What is this? The variables chairs and sport are marginally independent. What is this? Now we are going to implement following the Bayesian independent assumption. So now we are trying to decouple the parent and the child according to the Bayesian random walk. That is, several independent statements we can bring. So the variable chair and the sport are marginally independent, but when back is given, they are conditionally dependent. So now I am going to chair and the sport and the back. Chair and the sport. As this is, if you consider, it is independent, correct? But when you give a variable back, then they are conditionally dependent. If back is not there, chair is a different entity, sport is a different entity. You agree? This relation is called out explaining away. Okay. Now we are going to, when chair is given, worker, back are conditionally independent. Now, once chair is given, this workers and the back are conditionally, what is this? Conditionally independent. Okay. When a chair is given, workers and back are conditionally independent. When back is given, ache is conditionally independent of its ancestors, chair and sport. Okay. So now, when I am coming to this back, ache and chair and the sport, okay. When I consider this, it is dependent only on back, but this ache is independent on chair and the sport. The back is given and the ache is conditionally independent of its ancestors, chair and the sport. So the conditional independent statement of the Bayesian provides a compact factorization of joint probability distribution. Now I am explaining the joint probability distribution. Okay, what is this? Joint probability distribution. Suppose you have a chair, you have a sports, you have a workers, you have a back, and the A, it's an all variable is giving one probability. What is this? Okay, from this one, we start from the chair. Okay. we have a probability for the chair. Knowing the probability of the chair, we are going to work on the probability of sport because it is in the same level. Okay, we are going to work on the okay, sport. So now, knowing the chair and the sport, we are going to work on the probability of the W. 1 and 2, knowing this only, we are going to work on this. Okay, because this is a third event now. Now, again, you keep on adding. So after this, okay, workers. Then after knowing chair, sport, and the workers, then you will understand about the back. After knowing all these three, B, W, S, C, you are going to understand this, A. So now here, every state except this P of C is dependent on other state, having the knowledge of chair, having the knowledge of the sport and the chair, having the knowledge of worker, sport and the chair, having the knowledge of back, worker, sport and the chair. Correct? So if you use this comes like this. What is the, if you use the joint distribution probability, this is the factorization. But instead, now you are going a conditional independence in the base. And what does it mean? That if A is considered, only back is the parent. They are not coming into the picture. Understand? So what is that? The dependency. The dependency is released if you are using the Bayesian definition in the form. So P of C will come as it is. P of S will come as it is. Okay, because what is the relation of S and C? There is no link. S and C, there is no link. Okay, so there is no reason to include this. Okay, if this is a direct probability distribution, it comes like this. Otherwise, it is only P of S. Okay, but now for the workers, who is the condition for the workers? Only chair is the condition. So you should know only C to understand the W, not S and C. Understand? To understand only P, you don't need WSC. You only need sports and the chair. Okay, back. Only sports and the chair. Okay. So now, so all these things comes under, so P of C, P of S, P of W, P of B, then your P of A with respect to all these things are not needed because we only have the A. A immediate parent is the back. So only we limit until this. We will not worry about the rest of the people. So this is the conditional independent states. The probability of this Bayesian network simplifies the dependence of the probability when you are using this Bayesian network. You all agree what I'm saying?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay. So note that the Bn form reduces the number of the model parameters which belongs to the multinomial distribution. So such a reduction provides great benefit from inference for understanding, learning, and computational perspective. So the resulting model is more robust with respect to bias variance. So this is a more robust. We are not like every dependent statistics and we have to go with the analysis of variance analysis and all these things are not coming in the Bayesian. So now the back cake being separation, predictive inference, and one of two classes. Okay, so now I think the separation is not needed. Inference. Okay. Learning. Deep learning. Okay. NP heart problem, we are not working on this. Probably, I will only take this. Okay. Where is the figure 1? Okay. Now, the same, whatever we have discussed in this slide. In this slide. Whatever we have discussed only, it is here in this slide. What is this? Given in the figure 1, one might consider the diagnostic support for the belief of a new uncomfortable chair installed at the person's office and given the observation that the person suffered from backache. This is the explanation, whatever I was talking here. This was given in the paper, that's what I put it. Because, when you go with any probability, now we will take the probability when the probability of A is true. Okay, then what is the probability of A is true? When the probability of A is true, whether the chair is also true. Okay, so probably there is one, I think some slide I am missing. Just 1 minute. Probability. There should be some slides. Okay, that is on the back. Okay. See, these are the introduction class I think this is the one I was missing. I will explain this now. I think these 2 slides. Yeah, these 3 slides are very important. This is the basic calculus. So the basic calculus, the basic concept in the Bayesian treatment is that conditional probability. What is this conditional probability? Given the event B, okay, and everything else known is irrelevant, then the probability of A is X. So what we have given the event and we have to identify the probability of A. Let us say this X, okay. But the fundamental rule, normally everybody knows that P of A comma B is equal to P of, okay, now they have given it in the term of P of B. They should know P of B. Then, knowing the P of B, you have to identify P of A. Or P of A, and knowing the P of A, you can identify P of B. Okay. So, the equation, the probability of joint distribution is same. What does it say is that? Either it is you know the probability of B, then come and analyze. Or you know the probability of A and come and analyze the P of B. Both are talking about the joint probability of A and B only. Okay. So if you are taking this equation, what happens is probability of B, knowing this with this, then you have a probability of A. Then you can understand the other condition. This is the equation. You can simply, just replace it. You understand the logic, students? Everybody, are you online or not sleeping?
Yes, sir.
What is your
Yes, sir.
What is your sleeping time?
10:30, ma'am.
Who is the person?
Satish.
Satish. Satish, you cannot sleep 10:30.
Okay, ma'am.
Now your semester is coming. I'm more guilty that I could not take your classes. I was very much distracted by this COVID infection. Do you know that I got COVID? And yesterday only I came to my hometown. I was not able to talk. And today I'm little comfortable. I thought immediately I'll take the class.
Okay, ma'am.
So you will please listen to me, otherwise I will not disturb you guys in the late night.
No problem, ma'am.
Yeah. I didn't expect that I'll be off for 1 month. As a, it was a very tough period for me. Okay, so now this is a you know this definitely because this is the basic thing in a conditional probability and a joint distribution of the probability. So either way you can understand. If you know the probability of A, you can use the formula. If you know the probability of B, what you have to do is this will come here P of B. Okay, here you will have all the things with the P of A, P of A. Knowing this A, you should go with the P. So this is the basic. So now, what is the factorization? This was I was explaining. So you have a probability distribution P of A, and every state will have a substate. Okay. So every substate only will indicate the A array. So you have a problem. You have a AI and you have a different variable. And if you want to factorize it all over the BI, that is the second variable, what you should do? Then P of AI is the variable, then P of AI with the known value of B1 plus P of AI with the known value of B2. Like that it should go. So the notation, this is P of A is equal to, you are going to summarize or sum all the B variables keeping this AI for an independent state. So your summation goes along with B, and now you are going to have a P of A comma B. You understand? This is factorization, or we can say it's a marginalization. This calculation is called a marginalization, and we say that the variable B is marginalized. That is, the influence of B over the A is completely identified. This is the meaning. If they put like this, what does it mean? This is being completely worked out for the variable B, and you have to understand only the P of AI. Okay, this is the basic. So, when we have a Bayes theorem, Bayes rule, this is a conditional probability. Okay, Bayesians actually consider conditional probabilities as more basic than the joint probability. This will not consider joint probability. This will only consider the conditional probability. So this is one condition, this is another condition. Both condition talks about P of A. So if you use this, either of this equation, just before I was talking this equation. So sorry, this equation, okay, is the Bayesian equation. So now coming back to this, I was talking about the same Bayesian equation because we are worrying about the immediate parent. It's a conditional dependency. Okay, so you will have your A is 2. Then you have to have a summation of all other parameters, scores, workers, back, and the chain. Okay, all other summation. But you are only working on the A. Okay, so every conditional one, P of C, P of S, P of C with no P of W by keeping with the knowledge of C. Okay, knowing S and C, D. So these conditional probabilities will reduce the time and the dependency of other states if you use the Bayesian network. So you don't worry about all other things. Just whatever I teach, I will take it. The rest of the things, ignore it. We are not worrying with the D-separation. This is more on this. We have to go in elaborate, which is not required for your D-separation. Okay, so you should know until what is this example, what is this Bayesian equation. Okay, so Bayesian equation, this is the, what is the Bayesian equation? This is the equation, okay, Bayesian equation. If you explain this is the network. Okay, it's a conditional and the unconditional things are there. Okay, so it has no parents. Then its local probability distribution is said to be unconditional. No parents, no condition. Okay, if parent is there, you have a condition. Okay, you understand? It's a very simple logic which is connecting your graph theory and your probability. So we should know computer science to do the program. Probability theory mainly comes from the statistics, probably for some. Oh my god. So you should know the statistics. Okay, students. Today your what is that? Your you guys are there.
Yes, ma'am.
Yes, ma'am.
Okay. Base and network. You please refer this. This is some important thing which is really, you should know this. What else? So I will wind up this class with this now. Tomorrow, any possibility for me? Any possibility for me? Huh? See. Okay, so I have put it in your, what is that? In your materials. Please take the material and study. I asked you one more question. Tomorrow, can we have a class? No sound. Okay. You analyze, you study for your big data analysis. If any more one or two classes, if you give me, I'll be fine. Just let me know. Okay.
Yes, ma'am. We will discuss.
Okay, ma'am.
Okay. You discuss among yourself, and probably if you want one class in the morning,